inviting me. The subject of my discussion today is really about the if you like, the path where we developed over many years to reach where we are on data science and artificial intelligence. So the title is a bit fuzzy, where we talk about big data technologies, data science, AI, and many other things that could emerge in the coming decades. I don't know. But the whole aim is for knowledge extractions and science discovery and process understanding. When you understand process, it's in the sense of science discovery, right? So the content of my presentation, can you hear me? Yeah? Can you hear me?
Yes, we can.
Yes, we can.
Okay, so I'm going to talk about the fourth science paradigm, the emergence of IoT and big data. What is big data? The big data challenges that we've been facing for many decades, and the big data opportunities that emerge with affordable sensing and sensors anywhere, or with ubiquitous sensing, and also the affordable cloud computing, the new commodity that actually took us to where we are. And then when I will talk about data science and AI and the hierarchies of data science, and where does artificial intelligence sit here in this? Because we talk about data science and AI, but in fact, it's a subset of data science. AI sits somewhere, so we need to know where it sits. And then I will give some examples of science discovery and real-world problem solving under our ProBU research group, which stands for Processes and Behavior Understanding. So the elements of our research group work is on health, environment, security, and then I will finalize it with further thoughts, sort of finally, okay? Science focuses on investigation of real-world problems, mainly, while understanding the natural world and how it behaves. And it is founded on objective observation through measurements of phenomena, natural, nowadays industrial, of all sorts of that, and processes that entails with them. Experiments as benchmarks for testing hypotheses. So we come up with some sort of hypothesis, but we need to test it through experimentation. And we induce through reasoning for postulating general rules, or indeed conclusions drawn from facts or examples. And these things need to be repetitive. We need to show that they repeat. And we can even send or ask other colleagues to do the same experiments and see if they're receiving the same answers or similar answers or no answers at all. So we need to be open when we do scientific experimentations. So there is also a critical analysis of what we do. So the testing and validation of our hypothesis should be exposed to peer reviews and to be scrutinized, really. And that's what science is all about, science activity and conduct. It has evolved a long way, however, since ancient times. So in ancient times, science was based on empirical evidence. So information received by means of the senses, whatever they are, particularly by observation and documentation of observed patterns in situ. The word empirical comes from the Greek word for experience, empiria. Empirical evidence serves for developing a hypothesis in order to gain acceptance in the scientific community. And it has been practiced since ancient times in order to establish and understand facts, so-called truth, by ancient philosophers like Aristotle, as they are observed in field experiment. So we still practice this nowadays. I mean, we haven't given up empirical evidence. However, the scientific community sees it as only an early step in research prior to grasping the truth that is supposed or supported by first principles theories and more. So this is my statement that I did to my student 2020, so I put it here for your interest. Another ancient scientist working on empirical evidence was Archimedes, the famous Archimedes. Then we move to the second paradigm, which is guided towards establishing formal theories to explain what's going on around us. And this really emerged since the 1600s. You know, before that, we were working on empirical evidence. So formal theories really is about an explanation of specific aspects of the natural world that can be in science, that can be repeatedly tested. Oh dear, what is it? And verified in accordance with the scientific methodology. The methodology uses accepted protocols of observation, measurements, and evaluation of results that can be scrutinized by peers. The strength of a scientific theory is related to the diversity of phenomena. It can explain in nature while it remains elegant and simple. So that's scientific theory. When new scientific evidence is gathered, a scientific theory may be modified and ultimately rejected if it cannot explain new findings. It is then replaced by a more accurate theory. However, this doesn't mean that all fundamental theories that we have in place can be changing all the time. These events happen very, very early. But since the 1600s, we went across the generalization of relativity from the theory of gravity initiated by Sir Isaac Newton in the 1600 or 1700, and then generalized by Professor Albert Einstein in the 20th century. So this is a good example where we continued into the same science, but we generalize it so that by putting a new, more generalized theory explaining the gravity force. So that's around the second science paradigm. But things moved on. With the third science paradigm, it really started from the mid-40s after the Second World War, the beginning of the 40s to sort of post-Second World War until 1985. Really, this one was really computationally based. It is often known as scientific computing, or indeed scientific computation, and it uses advanced computing power and capability to solve complex problems found in nature, including those created by humans. It spans across many disciplines, but at its heart, it involves the development of numerical models with advanced simulation to express or monitor and predict complex systems behavior. It is radically different from experimental and theory, since it aims to gain understanding through the analysis of mathematical modeling implemented on computers. Because you see, with formal theories, you may be stuck in doing some predictions in time or space or any other dimensions. So you refer to the computer to do the number crunching for you, with some limitation, of course. But you have to have a mathematical model plugged in or programmed onto the computer. Usually requires a large amount of computation, which can be executed on supercomputers or medium sort of mainframe computers up to the mid-80s. And these are activities that were really championed by people like Alan Turing and later on by Professor Richard Feynman, who was a Nobel Prize, another physicist, although Alan Turing was a mathematician. And these two principal people or academics actually pushed the science paradigm to its third level. The thing is, if you like, the most important element here to work on the third science paradigm is to have a mathematical model. If you don't have it, you cannot pursue scientific computing. But then things moved on post 1985. So we moved to basically intensive computing, and supercomputers came in, vector computers like the Cray XMP in the 80s and so on. Supercomputer IBM Blue Gene, for instance, intrepid at Argonne National Laboratory, USA, and it runs with 164,000 processor cores using normal data center air conditioning, grouped in 40 racks and so on. Scientists carry out very, very heavy duty intensive computing, supported in a way by some theories, still pushing the calculation in new horizons, because even with those theories, we couldn't do a strict model to do the calculations. So I give you an example here in hadron physics, where I was involved in my PhD time in the 80s or late 80s, where we refer to the whole universe as a lattice, hypercube in 4D, space-time that is, and we kind of simulate it, and it would require, if you like, months and months of simulations and runs to achieve the answers, to get the answers. And in my PhD at the time, I was looking for the phase transition of hadron matter from free to confined matter, where we live in now. And the picture here was actually a turning point in my career as a student. I was first-year student. I'm sure you can find me, but I'll leave it up to you to find me. But this was a very important milestone in my career as a researcher. And I went to this Scottish University summer school funded by NATO. And we spent basically a month in St. Andrews universities, and we were taught by Nobel Prize winners and so on. Many groups came in, and it wasn't just physics, it was all disciplines using intensive computing. And we didn't realize at the time, but we were really the early generation of data scientists. I'll give you a clue. I sit next to Sir David Wallace. He's on my left. So in those days, for the first time, I started being taught that neural networks can be used to do some runs intelligently without trying to understand what's going on in the black box. And that was fascinating, because I was taught physics based on formal theories, and these are established by the big guys, Nobel Prize winners like Feynman and Einstein and all these people, bright minds. But then again, say, do we really need a formal theory to keep going? So in 1987, there was kind of vision seen by these people here that we're going to exciting time where we just need data. We just need data. We need observation. But the mathematical tools are being prepared now to be used. These mathematical tools could be just black boxes without waiting for another genius like Einstein to bring a theory to explain what's going on. So this is the change. That's the fourth paradigm. You don't need a formal theory to actually understand the phenomenon. You just need observation, and you need some mathematical intelligent algorithm to actually give you the output based on patterns recognition, basically. So the fourth paradigm on intensive really pushed on the 90s, the idea of using the concept of internet and new expanded rapid, all of this started happening. So the data generator environment was put in place in the mid-90s. And it led to the generate ever-growing vast amount of information and data very fast. And beyond the scientific research communities, basically data was being developed or generated across the board in multiple disciplines. So that St. Andrews University summer school where we met people from different backgrounds, not just physicists, although it was called computational physics, we nurtured or cross-fertilized our thoughts that we just need data. And the computers are there, and the mathematical algorithms are there, and we need to move on. So AI started being talked about. But I need to give you the history of what happened, more in depth. So with the intensive computing, businesses and government organizations led to the creation of large amounts of structured, semi-structured, and unstructured information at all levels. So this is all data, so we can employ all these kind of techniques to multiple disciplines. And as long as you have this vast amount of data needed to be processed, analyzed, and shared securely, obviously. The storage, management, access to processing of this vast amount is a fundamental challenge. So All this is an immense challenge. The requirement for searching, analyzing, mining, and visualizing this data became like the biggest challenge. So data science was born formally. So sort of across discipline. It wasn't like within a small academic community where we were, for instance, in physics. And it tends to address such challenges. So going back to affordable sensing, because that's the key. Affordable sensing started becoming available to everybody since the mid-noughties. We started introducing the concept of future internet. I was involved in this at European level, at least. So we created the concept of future internet, multiple internets, internet of content, internet of services, internet of people, internet of things. And the only term that survives was really Internet of Things, which meant actually the future internet for us that is now. So the Internet of Things is actually the future internet that we talked about in the mid-noughties. And you see, the pre-internet that was created in the early 90s, well, made popular, it was created in the early 60s, actually, 1960s, by the defense department in America, but became popular in the 90s worldwide, basically. First internet that I used was in 1990, I think 1991, 1992. The first search engine were already in place, but this moved on. And Internet of Content emerged, Internet of Services, like e-commerce and so on. All these started happening. Internet of People, social media and so on started happening in the mid-noughties and so on. And the Internet of Things is really anything that can have an IP is a thing. So we merged the concept of future internet and turned it to Internet of Things. But these are important elements in technology development, in ICT, because information communication technology, because these are the creators of data. And we moved from ordinary phone to smartphone. We also moved from desktop to services and applications. Equally, we moved from ordinary cars to smart cars and driverless cars nowadays. We all got connected with smart homes to smart things, including cities now. So all of this, all these are generators of data. These are things. Things generate data, and that is big data. So we have been flooded by a deluge of large volume of data from heterogeneous sources. These are heterogeneous sources indeed. And these are from all business sectors, public and private sectors. They generate proprietary data, they generate open data, they go cross-border, cross-administrations, they're multilingual, they're multicultural, ethically speaking. They are governed by multi-regulations. They have multiple semantics. So there are semantic conflicts and more. So the complexity is big. So big data is not just about big volume of data, but it's complexity. So what is big data? It's a term that has been used to express a collection of data sets that are so large and complex that they come from various sources. It becomes impossible to gather them in an ordinary traditional database. It also becomes impossible to process them at all. But where do you start? No one could operate on them nor make sense on them using traditional tools and applications anymore. So this is like early 2000s. These are sort of, we were stuck. In the mid-noughties, we started creating a jungle of data species. I call them species of different types and diverse properties and behavior. The data also has behavior. It behaves differently from one type of data to another. And they manifest themselves differently, meaning statistically, because they are from different origins and they also represent different phenomena or different processes. So welcome to the big data problem. So one of the big data challenges is obviously the volume. The volume, the digital world in which we live, is growing fast. The storage of such large data while maintaining its integrity and security is a big a big challenge. Access to such data rapidly and critically is another challenge, notwithstanding the processing of such big data in order to retrieve information of interest. So out of all this big data volume, we might be interested in some minute element of it, but how to get it. And the rate at which the world's data is growing is phenomenal. Up to 2020, also valid now. This graph gives you how we're growing exponentially. There's also the challenge called variety. Different species of data is being generated from diverse sources. So some data is structured. This is the traditional. So we have good control of how the data should look like. Semi-structured, that's uncontrolled, human text data. Unstructured imagery could be anything. And they're all mixed together in a big data jungle. So this is where we are now. Well, since 2005. And to give you an example in terms of another challenge is the velocity of this big data, how fast this data is growing. So for every minute, we have 100,000 tweets generated. 695,000 social status are entered. 11 million instant messages are sent around. 700,000 Google searches are triggered. That's every minute. 170 million emails are sent. 1,820,000 terabytes is created. And 220 plus new mobile users are created. This information is 2 years old. So this data basically is bigger now than what it was 2 years ago. There's also the element which is quite a challenge, a bigger challenge, which is the veracity of data. Data provenance, data ownership, data quality, data uncertainty, trust and trustworthiness on data. 1 in 3 business leaders do not trust the information they use to make critical decisions. So in a way, it was found that 90% of the data is basically obsolete. The problem, the 10% remaining, is mixed up with it. And this 10% is called value of data, another V. So the question, how would I extract good information from the remaining 10% of the data? So this question was asked in the mid-noughties by a famous man. Steve Jobs actually asked that. What do we do? We are in trouble. We don't know how to manage this data. I will need to filter out all the obsolete data from the big data stack. We also need to analyze the data first before we filter it out. But before we do that, we would need to pre-process the data and put it together so that we could analyze it in the first place. All this is tedious task. And we're not sure if we could scale these processing operations since data keeps growing and getting more complex in time. So that's the question asked by Steve Jobs before he passed. Well, it was a few years before he passed away. But he asked it to the Stanford groups, you know, the Californian people from Stanford University. I mean, these guys. So they knew there was something that needs to be done. And it has, of course, commercial incentives at the global scale. So the creation of cloud computing was, although being thought by academics, these guys thought how we can make it reality. And in fact, make it the new commodity. Basically, you don't worry about how to process big data locally, but you go in the cloud and use the cloud resources to do the work. And this idea was set up by some of these guys. Well, all of them and others behind them, of course. You know, people like Larry Page and Sergey Brin, the founders of Google, and Bill Gates and Jeff Bezos and Mark Zuckerberg, and all the teams, the huge teams they have, provide effective storage of data at large, sustainable scale, which can be accessible remotely. provide accessible tools to analyze your data even remotely. So all this was set up in the mid-noughties. So the opportunity is to turn the cloud computing resources as a commodity at the global scale. And it's a top case for managing the energy sector, for example. This is an example where intelligent monitoring of the distribution grid or optimizing unit commitments, forecasting and scheduling loads, optimizing it. Can you do that at continental level, for instance? And the big cloud facility companies nowadays offer such commodity to the energy sector, for instance. People like Microsoft, Amazon, Google, IBM, and more provide such commodities easily with access to big data distributed storage and parallel processing and analytics resources altogether. This is just the energy sector at the continental level. You know, for Europe or America or at the global scale, you can do that. Now it's possible. And this is thanks to this man, Doug Cutting. He is the co-inventor of Apache Hadoop. This became like attached to the cloud computing technology that the previous guys from Stanford thought about. But he and his team, his company, Apache, they did that in 2007. And basically the idea is how to efficiently distribute data, big data, through resources for storage and also through resources for processing, parallel processing. Parallel computing existed before, during our times in the 80s. When we went to this St. Andrews University summer school, 2 parallel computing centers were created afterwards, immediately, by the guys who were there, one in Edinburgh Parallel Computing Center, and the Parallel Computing Center in Southampton University. And I actually joined this center later on in my career. So I did a big loop from physics to sort of information systems in my career, and then moved to this Parallel Computing Center, which was renamed the Southampton University IT Innovation Center, where I was science director there for 10 years, and then joined Bournemouth in 2019. So that's very quick think about my career here. But the question is, what happened in 2008? Cloud computing commodities became affordable to implement with ever-growing big data V's, you know, the velocities, the volume, the velocities, and so on. This became immediately manageable thanks to Apache technology, as well as the other Stanford group. So global IT infrastructure was put in place and became available. Core application designed to support decision-making groups, you know, people for the grid or for defense or anything. Cloud services for on-demand and secure data access and analytics became reality. Ad hoc connectivity to these resources and reconfigurability in place, no problem. You can do it on the palm of your hand using your mobile phone. These are mostly available as commercial commodities nowadays. And they are currently led by the big global corporations such as IBM, Google, Amazon, Oracle, SAP, etc. So with that, in 2008, data science and AI became possible to combine. I mean, data science and AI to combine, and formally launch with confidence post 2018. So that's what happened, because ideas of AI existed since the 40s with Alan Turing. Data science really started happening in the 80s. But in 2008, with cloud computing technology becoming a commodity, by 2008, we were ready to launch all of this. And it propagated everywhere around the world. And the universities took this discipline as a new discipline. In fact, when I was in Southampton, I proposed this discipline to emerge. I proposed it in the early 2011. And now there is data science and AI in Southampton, as well as Bournemouth and so on, and many universities around the world. So the question is, what is AI? What is artificial intelligence? Artificial beings exhibiting intelligence appeared as storytelling creatures from early ancient civilization to the present time. We always thought about that. And these characters also raise many of the same issues, which are now discussed in the ethics of AI. But the study of formal intelligent reasoning, known as mechanical reasoning, started with some philosophers and mathematicians since ancient Greece, with Aristotle basically again. And this went on quiet for many, many, many centuries. This carried on without serious progress until 20th century, when computer machines were built in the 40s. With the study of mathematical logic, this led Alan Turing with the theory of computation, who suggested that computer machines could simulate any possible act of mathematical deduction. So digital computer could simulate any process of formal reasoning, known as the Church-Turing thesis. So this thesis, along with concurrent advancement in neurosciences and information theory, this has led researchers or academic researchers to consider the possibility of building an electronic brain, if I may call it. So the first work that was recognized as AI was by McCulloch and Pitts in 1943 with the formal design of Turing complete artificial neurons. And there is a famous paper in 1943 by these two guys at the top. So with the access of digital computer becoming possible in the mid-50s, AI research began to explore the possibility that human intelligence could be reduced to step-by-step symbolic logical manipulation known as symbolic AI, also known as good old-fashioned AI. Some research pursued this idea in 1956 at Dartmouth College in New Hampshire, not to be confused with Dartmouth in UK. But the approach based on symbolic AI was virtually abandoned in the early 60s. So symbolic AI basically froze and it was abandoned. Then AI crossed an Irish desert until the mid-80s. Basically, there was no funding on AI between the mid-60s till the mid-80s, another 20 years, when the idea of building intelligent systems, basically computer-driven systems, started emerging in the 80s again in the private sectors, corporations. Large business corporations started to use big mainframe computing for running their systems. Large business corporations started adopting systems with simulated human operation administrative processes. They tried to mechanize these kinds of processes intelligently, and AI was resurrected. And new funding for these corporations became available for academics, which is a eureka moment for them in the mid-80s, mid-80s. So AI was back, and supercomputers were being built in the mid-80s. Scientists were doing some work, and they grasped these kinds of technologies to do their runs. So the fourth paradigm converged with this, where we needed to do intensive computing while funding is being available, and AI was also developed by mathematicians. New algorithms were being developed and so on in the 80s and 90s. So in a way, data science, as I said, was born in 2008. Data science and AI was born in 2008. But with all this stuff on data science, a strategic data management framework needs to be put in place for performing data science and AI. And the aim is for knowledge discovery, knowledge extraction and science discovery. The whole aim is for extracting knowledge, those 10% that we're after, that give us the emergence of new, understanding new phenomena, which is new knowledge. So we would need management and control of data under comprehensive policies and governance guidelines, including ISO standards for monitoring systems. This is not like the exciting stuff for me, but we need to go through that. We need to capture and extract structured and semi-structured and unstructured data from trusted sources as well. Then we will be able to perform some analytics for delivery of the right extracted knowledge, the 10%, so-called 10% of big data, and capture a situation awareness to the right people and deliver it to the right people at the right time critically. A good example where big data technology was put in big time and AI was put in big time was during the COVID-19 pandemic for delivery of information to the SAGE emergency group in the UK and other countries as well. It was a very cooperative activity in a very, very tough time that went on for 2 years and achieved the result. So what hasn't been said was the big data technology was actually capitalized upon and explored and exploited to actually run very fast in critical time. I mean, if you compare the pandemic that happened in the 20s, which is a respiratory problem as well, like COVID, the Spanish flu, it went on for many years, and the damage was much bigger than what happened, what the COVID-19 pandemic did to us. So in terms of hierarchy, data needs to be pre-processed. You can't avoid that. So you need to do quality management in data. You need to agree on metadata standards. You know, there are some metadata where actually I'm involved in these international committees like OGC, the Open Geospatial Consortium, or DGGS. This is another way where I chair it. The discrete global grid system is been proposed for the last 5 years to actually provide geospatial data under this grid system because it goes nicely with data mining, big data mining. Provenance and trust, you know, where does the data come from? Who owns it? What's the level of trust and trustworthiness? Removing the semantic gaps, the conflicts, we need to be reconciling them. The gaps removals, the asynchronicity and multimodality of data. Data comes from different wavelengths, from different observation platforms at different time frequencies and so on. So all these are called data preprocessing. And there are specialized data scientists who just live on the low level. But you've got other higher level. Data post-processing. Here, there's the science of sort of how you can harmonize and aggregate data and under a trust metric to put it together and start creating new data. So there's a primary data where you can start doing research on. So there are people who are specialists in that. You know, you could have multiple gridded data and you need to aggregate data on one grid. So you need to do some manipulation of data. That's what kind of data fusion at this level. There could be a different time, but you harmonize it. You can multiply. You can have a kind of weighted trust to each of the data, so that you create a multiple weighted trust, and you will end up with one specific trust, or emerging or fused trust. Then the higher level of academic endeavor here on data science and AI. Well, I'm calling AI, but it's still data science here. Data mining and expert clustering, background extraction, foreground detection. So this is where you bring data and you start distinguishing a foreground from a background. And the foreground is the new stuff that you might be able to actually monitor and track, understand how it behaves. You see how data is being organized within the big data jungle. We have a very disorganized data, and we turn it into an organized, structured. Well, I don't want to use structure, organized data. Irrespective of its structure, structured, semi-structured, unstructured, all together. So, and then you move to machine learning, where the foreground data that you detect, you want to process them and try to understand how they behave. So you deploy machine learning techniques to actually track them, understand what they are. So you want to classify them, what they are. You know, I could have an image where you have tasks to, for instance, track a human being walking and try to understand what they're doing, for instance, or recognize a cat from a chair or and from another object. So object recognition. And then you want to go further. You want to perhaps anticipate where these things that is moving in time and space, where is it going in the future? So you can proceed to higher level than level 3, where you can model the actual foreground data that you track and detect and understand, and predict where they're going and even reason upon them. Reason meaning that you have some sort of knowledge model and you say, what's going to happen? I'll give you the idea why I'm talking about that, because we specialize in behavior in our group. For instance, we anticipate on behavior because we understand it using machine. So in all of these levels, I put this kind of ellipse where AI sits, because I asked where does AI sit in this hierarchy of data science. So you can see data science and AI, but from level 2, 3 to the high level of reasoning, AI can be there. Okay. So again, currently AI is being deployed in all aspects of our living and problem solving. And AI is now in charge of solving the so-called real-world problems. That's definitely its purpose, real-world problems. And we have so many real-world problems, cyber nature, like cybersecurity, physical security, finance, gaming, robotics, social media, healthcare, transport, environment, and more, education, and so on. So this kind of figure shows you where AI is putting its hand on, and it's everywhere. And I don't know if you can see that, but perhaps I can. Oh. Do you see it? Can you say yes?
Yes, yeah, you can see it.
Okay, so I'll move to kind of PowerPoint. Yeah, I forgot to do that. But you can see all the disciplines that are working together on AI and where AI is sitting. It's everywhere. And these are all disciplines in computer science and related disciplines to computer science and information science and so on, and engineering, really. So it's progressing, AI is progressing into a huge number of branches and sub-branches with the diverse and exciting applications. So I'm putting a smile because I like that. I'm excited about that. Let me give you a bit of examples of science discovery, real-world problems that are being done by our group. We are working on human health, for instance, and these are examples of questions that we put in, we throw at our group. What are the main processes that likely lead to neurodegenerative diseases? As an example. How can we understand the process? What are the causal processes that lead to that? What are the core gene expressions that influence the development of chronic respiratory diseases? This is a big thing, like COPD, chronic obstructive pulmonary disease, or asthma, and so on. We are doing that. And what are the environmental conditions that influence exacerbation events in the above two health conditions? So the environmental conditions actually influence, the environment where these patients live have a say on their conditions. So people with respiratory diseases could be more, if you like, sensitive to polluted areas, atmospheric, atmospheric pollution areas, or even just the winter season. Neurodegenerative diseases could be some chemicals, could be anything. We don't know, but we are exploring that nowadays. Another disease, what are the core gene expressions that influence the development of the Waldenstrom microglobulinemia yeah, which is a rare blood cell cancer. We're working on that as well with Dorset University Hospital, with the NHS people. So this is all exciting stuff. So we currently have 3 PhDs on data science and AI researching on the above issues. So our group is excited about this work, and we are publishing on this, and we are progressing very fast on this. This is an example from a paper we recently published, led by our PhD student, Tim Albiges. You can see the details of the paper. Here, we can distinguish 3 respiratory conditions from two respiratory conditions from COPD. So we specialize in COPD, as I mentioned earlier, and we distinguish it from healthy patient to another patient who has another respiratory condition as pneumonia. And the results are, these are the ROC curves that actually, and there are various components of breathing signals, human breathing signals that we have, which is data, and we are able to correctly classify the condition of COPD with good accuracy. So this paper is a flagship paper that we published last January, well, a few months ago. Another application of science discovery, real-world problem solving, is concerning the environment. The question that we threw out our group, for instance, what is the impact of climate change on animal behavior and habitats? That's I mean, climate change is also affecting human placement. People move when there is no food, as well as animals. So we studied ocean species and how their habitats are changing. And basically, we're trying to understand their behavior from the oceanic and atmospheric changes due to climate change. There's also a question that we haven't solved yet. What is the impact of microclimate forecast in urban social behavior and local businesses? That could be a PhD. So if anyone has funding, please come back to us. And another question, what are the safest time windows, spaces for patients with respiratory conditions to move around the town for the daily activities? There's more. There's also a question. There are also a question that we can create together. So this is an example of migration trends of loggerhead sea turtles in the west coast of Africa that we did in 2017. The data was from Copernicus satellite observation data. Basically, the oceanic data parameters have been changing, and these species, loggerhead sea turtles, started changing their behavior, going where there is food, where they can mate, and where they can find safe refuge to live. They are changing. And we did that on other species like the albatross and also the yellow fin tuna. They migrate, the yellowfin tuna, I haven't got the pictures here, but we did that under this paper on the IFIB Advances in Information Communication Technology in 2017 with my team in Southampton, actually. But we are continuing and doing that in Bournemouth. There's also security that we do, and this is physical security, cyber security, or combined. Can we predict and prevent intentional malicious behavior, for instance? Can we detect unusual seed behavior and prevent its propagation in crowds? Can we scale in the above detection of human behavior and understanding in large crowd systems, large network monitoring cameras, for instance, used for observation? The cyber case, cybersecurity, can we detect malicious behavior in cyber communication transactions? Can we detect early symptoms of cyber attacks? Or can we prevent such potential attacks critically in time? And we can combine these two ideas. Can we fuse the above types of detections and reason upon them for advancing situation awareness? In fact, attacks now could be of cyber physical nature. So you basically there have been attacks in some cities or some sort of city centers in the last 10 years where the cyber environment was blocked before the attack, the physical attack happened, which is basically a terrorist attack, which was very, very concerning. But with the technology, we are able to prevent that. In fact, understand the intentional malicious behavior early enough to actually prevent it to happen, both in the cyber world and the physical world. But we need to bring these together.
Sorry, Professor, I have to interrupt because of the time, because I know that people might be interested to ask you a couple of questions. I'm so sorry to interrupt you in the middle.
Yeah, I agree. It's a long presentation. This is an example where we look at crowds in a stadium. We did that in Spain. You've got all the papers. We did that in 2017. And then another one we did not long ago in October 2022 in area. Basically, we understand crowd behavior and we move to intentional behavior and so on. So this is related to a large project we won at Bournemouth. The previous one was called Evacuate when I was in Southampton, but this one is Bournemouth. We completed it. It's called S4 Cities. It's an exciting project we did, although in the middle of the pandemic we did it, and it was the most successful project I've ever seen. And we received the congratulation from the European Commission on that. So these are all the papers we produce with the S4 cities. I think my final thoughts on this: data science and AI as a discipline has emerged as an important branch of computer science for addressing real-world problems. Under the realm of the fourth science paradigm, we are into interesting times. These times are for much accelerated science discoveries, but the aim is to use it peacefully and wisely for humanity's benefit, such as the eradication of diseases, poverty, and enhancement of safety and security globally. This will be done, can only be done under consensus of ethical and legal frameworks and values when it comes to the use of data and data protection for pursuing research and development. Thank you very much.